Okay, folks. Hopefully you can see this okay. So the plan for today, this lecture, I'm sorry for doing this lecture a day late. I had to give this talk at the March meeting, the American Physical Society March meeting yesterday. So today, I want to give an example. I want to continue our discussion from last time. And our discussion last time was, we were talking about Fermi's golden rule. That's what we derived last time. And so today I want to do an example of that. And then this will lead into the next topic, which actually two examples, and one of which is broadband absorption, broadband light absorption. And then this will lead into a discussion of optical selection rules. Okay, that is the plan. So this is all pretty important topics. Okay, so let's see. So last time we derived Fermi's golden rule. And then this was what we derived. We had some quantum system with some discrete level, and we'll just call that the initial state. And then we had some sinusoidal perturbation. H prime equals, what do we call it? H prime sine omega t. Let's call it H prime of t. And then the idea was if omega gets us out of the box, then we have a continuum. If we have a continuum of states that we're transitioning to, so it's basically, the idea is that we have a discrete state and we have a perturbation which takes us to some continuum levels. And that's the setup, and it's actually more common than you think. So you might think that that's very specific, but it is very, very common situation in physics. And so the question then is, what is the rate of transitions? And so the probability to have the transition, probability of transition to some final energy, it turns out at some time t is equal to some rate times t. And so then what we do is we say that the probability of the transition per time is equal to the rate. And that's a really important concept, the rate of transitions. And the rate of transitions is equal to pi over 2 h bar times the matrix element that connects the initial state to the final state squared times the density of states at the final energy, where the final energy for the sinusoidal potential, the sinusoidal perturbation is the initial energy plus h bar omega, kind of what you would expect for absorption of a photon. And this matrix element connecting the final initial states is this. It's just sort of what you would expect. the matrix element that connects the initial and final states. And I will just make a little note here. Let's make a little note, which is that if you're Fermi's golden rule works for actually a number of different scenarios. For example, if you have your sinusoidal perturbation, I'm sorry, if your time-dependent perturbation is just a constant that just turns on and then off at some time t, and it turns on at t equals 0. So this is our, seen this before, if it just turns on and then as a constant, then what happens is you have, and I should say also, if h prime of t is equal to h prime e to the I omega t, which is actually sort of unphysical, but very common in physics. It's very convenient. Sometimes we like to do a Fourier transform of our perturbation, and so then we like to say, well, how does each Fourier component of the perturbation influence our quantum system? And it's a useful concept mathematically, but it's sort of unphysical because that gives us a complex Hamiltonian. H prime is complex, but we do it anyways. And you're used to that because, you know, when you talk about calculating the impedance of a circuit with inductance and capacitance, we often will do every, you know, and you talk about simple harmonic oscillator with dissipation, you often will solve it using complex numbers and take the real part at the end and blah, blah, blah. You've done that before on physics. So we sometimes do this anyway. I'm not going to do it in this class, but out in the real world, people do it since mathematically convenient. And the point I want to make is that for both of these cases, then you can derive Fermi's golden rule, but you're going to get a slightly different answer. You're going to get, instead of h bar over pi, instead of pi over 2h bar, you're going to get 2 pi over h bar. The constant is a little different. Okay, and so then you're going to get the same thing, but a slightly different constant here. There's a factor of 4 difference, and that's just buried in the math somewhere. And the only reason I'm mentioning is because sometimes you're going to see Fermi's golden rule written in this different way, and you're going to wonder why it looks different than what you learned in class, and that's why. If you have these different types of perturbations, you get slightly different prefactors. Okay, but let's not worry about those nuances. And let's now do an example of Fermi's golden rule. And the example that I would like to try, the first example, is let's design a burglar alarm. Because we're really worried about burglars, right? You never know; they might get you. So let's make an alarm so that we know if they're on their way. And so, okay, so here's the deal. Let's design a burglar alarm. And so we're some kind of electrical engineer, and we realize that we can get a semiconductor material, some weird semiconductor, I don't know, it's germanium, gallium arsenide, silicon, something. And we have impurities in our semiconductor. And we put a battery on it. And we have this great idea. We're thinking to ourselves, hey, I can put a battery on my burglar alarm. And if I put a battery on this thing and measure the current, then then what I can do is I can have a laser here and shine light at this. And what's going to happen is this is some voltage, and then I can have this go to some, you know, alarm controlled by a computer. The current, it's measuring the current. And so then what happens is if light is on, then alarm is off. But if light is off, then I can turn my alarm on, and I can make a loud noise and scare away the burglar. Because if the burglar steps in front of the light, so I have to detect the light. So I must detect light to make my burglar alarm. Okay, and so the idea then is that the idea is that the light will hit. These are impurities in my silicon, and so the impurities look like little boxes, and the electrons are stuck there. And then if the light hits the silicon, it's hitting those little impurities, and then it's causing the electrons inside of them to go out, h bar omega. And then I can detect that as electrical current in my circuit. So when those electrons jump out, I can detect them. But then the question is, what is the current? And suppose that I know, and so I'm an electrical engineer, so you have to know what's the current, because you have to detect the current. So you have to know which little circuits to buy to have the proper amount of resolution and sensitivity. And you need to know it, and in order to see if it's economically feasible, to see if you can make money, because the whole point is to make money. All right, so you have to use your quantum mechanics because you want to make money, and quantum mechanics is going to help you to make money. So the point then is that you know the laser. So let's assume that the laser is going to create some Hamiltonian. You know the frequency of your laser, and you know the strength of your laser, because if h of t is equal to h prime of t sine omega t, then you know what h prime is, because you know that, whoops, it's going to be like this. It's going to be h prime sine omega t. So then you know that h prime is going to be the charge of the electron times the electric field of the laser dotted into this vector r, right? Because that's just force times distance work. So that you know the h prime, and you know the frequency of the laser. And so then you want to know what is the current that the laser then creates in your device. And so the current then is going to be, you know that for one impurity being hit by that laser, there's going to be some rate at which there's going to be some rate of transitions, rate of transition. And so then I know that for one impurity, the rate is equal to the number of transitions per time. And so then I know that the total number of transitions per time, the total number of transitions per time is going to be equal to the rate times the total number of impurities. And suppose we know the impurities, because we can buy, you can buy silicon with a certain number of impurities. You just buy it. It's, you go to the website of the silicon manufacturer, and you just dial in how many impurities you want. I've done that. You can actually do that. And so that's the total number of impurities. People do that all the time. And so that's why they call it Silicon Valley, because there's a whole valley full of people who make silicon, and they all have websites so you can buy their silicon. Okay, so that's the total number of transitions. So then that means that the electrical current that you detect is going to be equal to charge, which is minus E, per impurity, times rate for one impurity, times N, the total number of impurities. Okay, so you can see that that's my electrical current because that's going to be the total charge per time, which is equal to current. All right, so that's how it works. So we know all these things, and so to find I, the one thing that we really need to calculate, we need to find the rate. That's the one thing we don't know. We know the total number of impurities, we know the charge, but we don't know the rate yet for one impurity. And so that is what we're going to calculate using Fermi's golden rule. Because we want to make money. Remember, the whole point is to make a burglar alarm. And so to make that burglar alarm, we got to know what that rate is so that we can know whether or not the current that is generated is detectable or not, and what electrical circuit we're going to need to buy to detect that current. But to know which electrical circuit to buy, we need to know how much current, because if it's a microamp, I'm going to buy one circuit, but if it's a nanoamp, I got to buy a different circuit. If it's a milliamp, then I got to buy a whole different circuit. So we got to know what that current is. Okay, and to know the current, I got to know that rate. Okay, let's calculate the rate. So the rate is equal to pi over 2h bar times the matrix element connecting the final and initial state squared times the density of states at the final energy. So we just got to calculate this for the situation at hand. That's Fermi's golden rule. So we got to calculate it. So we need two things. We need to know what this matrix element is, and we need to know what this density of final states is. So let's calculate those two things, and then we'll know the rate, and then we'll know the current, and then we'll know which circuit to buy, and then we'll make a bunch of money and stop all the bad burglars. Okay, so all right, so let's do it. Okay, so let's do it. So now what we're going to do is let's set it up. And so let's find the matrix element. And we know what that is. We can have some final state, and we're going to have our perturbation, which is E times the electric field of our laser, which we know because we bought it, times the operator, the position operator, hitting the initial state. So we gotta calculate this. And so let's do the situation. And so what's going to happen is we have, the idea is that we have some chunk of silicon with a lot of impurities in it, and that chunk of silicon has a length, and then it goes to our our battery and our current meter, and it's an electrical circuit, and the light is hitting it. Now the light has a polarization. Let's just say that let's assume it's polarized in the z direction, z hat. And so already we can see that this is going to be, I'm going to write it like this. Check this out. I'm going to write it like this: E minus E, E naught dot, how do I want to do this? Minus E naught dot final minus E R initial. I'm just rewriting it a little bit. And the reason I'm rewriting that is because something just to notice, just a silly little thing to notice, is that if I write it like this, then I can see that this is the dipole operator, because the dipole, remember, for an electric dipole, the electric dipole of the system by definition is the sum of all the charge You go to every charge in the system and you multiply the charge times the position of the charge, and you add it all up, and that's the dipole. That's the definition of electrical dipole. And so if you just have one charge, like one electron, then the electric dipole is equal to just minus E times R for one electron, which is our situation. So the point I just want to make is that H prime is equal to minus E naught time dotting with the matrix element of the dipole operator. And so you're not maybe used to thinking like that, but it is what it is. So it's the matrix element of the dipole operator, the electric dipole operator that's connecting initial and final states. And this is actually, you might never have thought of it like this, but this is a really important way to think about it. This is how people who do optics and lasers, they're always talking about dipole matrix elements. And so it is a big deal. And so that's the, damn it, stupid thing. So that's the dipole matrix element. Okay, so that's really what we have to calculate here is the dipole matrix element, because so we have, but in our case, the light is polarized in Z, and so for us, since the light is polarized in the Z direction, then we have that the matrix element is equal to this final, sorry, the matrix element, let's get everything right, is going to be equal to minus E naught times the final minus Z initial. Okay, so that's, well, actually I don't need to do all those. Just make it simpler. It'll just be E naught final Z initial. Okay, so that's what we have to times charge. So that's what we have to calculate. All right, and so then we have the, and so if we look at one of the, so if we look at one of these little guys, these impurities, then it's living, what's happening is the impurity is living in a, in some state, I'll call it phi initial, and just make it a one-dimensional state, even though it's actually three-dimensional, but we can do this in one dimension. We can just assume there's some simple function that describes the impurity state, which is known, because people have figured this all out a long time ago. Impurity state is known. It's a known thing. So let's assume that we know that impurity state. And the energy of the impurity state, epsilon, is a small number. We'll call that a shallow donor, meaning that the energy, the binding energy of that state is small. So then epsilon is small binding energy, and small compared to the light. We'll just say that h bar omega is way bigger than the binding energy of the impurity. And so what that means, what that all means is that when the light hits it, it takes it out, it takes the electron out to some, I shouldn't have done that. Just get everything collided. What that means is that when it takes it out to its final state, h bar omega, then we'll say that that's the final energy. And we'll just say that the final energy is equal to approximately h bar omega. Since h bar omega is so much bigger than epsilon. Okay, so that means that we know, we know the final, so that means that we know the initial state, we know the final energy, but what about the final state? We need to know that final state. That final state is this, because what's going to happen is, the way to think about it is I have some impurity which has that electron trapped, but once the electron gets out, it becomes a free particle state. And so that's the final state. So the final state is just a free particle state, which is just a plane wave, e to the I kx. But I have to normalize it because the math gets funky. So I got to normalize things. So let's put it into a box of length L. And so then it's 1 over square root of L. I've normalized it. So it's a box of length L. That's the chunk of silicon that I bought from my manufacturer. Okay, so that's my final state. So then it all makes sense. I got everything just about 1 over square root of L e to the I kx. And so that means then that my matrix element connecting my final and initial states, now I can calculate, because it's going to be E and the electric field, and then it's going to be this final Z initial. And so I know how to do it all now, because that matrix element is just an integral. It's on the left is the final state, the complex conjugate, e to the minus I kx. In the middle is that operator Z, and then on the right-hand side is the initial state, which is my impurity state, which I know because I looked it up in the book, and I got to do that integral. So I'm done with that. So I'm done, because I'm just from 0 to L, the size of the box. Okay, so because integrals are easy. Once you have a definite integral, you can plug it into the computer or whatever. So let's assume that that's done. But then the thing we're missing, but we still need the density of states, which is really h bar omega. What's the density of states at h bar omega? And so that's a little bit tricky if you've never done density of states before. But I'm assuming that you all have done density of states. Maybe you haven't. I don't know. But let's do it. So calculate density of states. Now, in case you've never calculated density of states, then this will look really weird to you. But if you have, then it should just be review. But density of states is a very important concept in physics. And so if you've never seen it before, then this is your lucky day. You can learn something important. All right, because density of states is a big deal. It's used throughout physics, and so, but when you see it for the first time, it's a little bit weird. You know, it's one of these tricky concepts that is not obvious. I mean, once someone explains it to you, it's kind of simple, but it's not obvious. It's one of those. I think it's sort of a tricky concept the first time you see it, but here it is. Okay, this is the concept of density of states, is that rho of V equals density of states, which is equal to the number of states per energy. And the number of states per energy, and the idea is that the number of states in this range, and I defined this before, but I'll just remind you, in the range E, that's the here, let's do it like this, E minus delta E. Let's not use delta E, let's use E minus DE over 2E less than E plus dE over 2 is equal to rho of E dE. All right, so that's the number of states in that interval, dE. So it's basically, I have some interval of energy, and I'm saying how many states are between E and basically E plus dE. Okay, so how many states are here? Number of states. And the number of states is equal to the density of states times dE. All right, so that's sort of the definition. And so now I have to calculate what it is. And so here's the way to think about it. So let's consider a free particle. And the density, you can have density of states for different situations. If I have a crystal, what's the density of states in the crystal? Or I can have a free particle, what's the density of states for the free particle? It just depends on your Hamiltonian on your system. Every system is different, has a different density of states. But let's talk about free particle, because here, the final state is a free particle in the silicon. Free particle in my silicon. And so we're going to assume that the silicon is just like a vacuum, which is actually not too far from the truth. And so once the particle is moving freely in the silicon, it's like a free particle. And so for a free particle, we know that the energy versus wave vector is E equals h bar squared k squared over 2m, a parabola. And so the idea is that we quantize, the idea is that we know that the states are quantized in K. And why are the states quantized in K? States quantized in K, that's the starting point. Starting point is to recognize that states are quantized in K. That's always the starting point. And it's really simple to see, because if I have a box of length L, then I need to have periodic boundary conditions. Periodic boundary conditions. In order to describe what's happening mathematically, it's convenient to have periodic boundary conditions. So we always like to connect the ends of our box. And that means that we need an integral number of wavelengths. Integral number of wavelengths in box. All right, and so that means that this is the longest wavelength. But then there's also shorter wavelengths. That's the next shorter wavelengths, right? And then there's the next shortest wavelengths. You see this? You see this trick, what I'm doing? And so what that means then is that if I take the length of the box, then it equals an integral number of wavelengths. That's an integer. And so that means then that lambda is equal to L over N. But if lambda is L over N, we know then that K is 2 pi over lambda. So that's going to be 2 pi over L over N. So that means that K is equal to 2 pi over L times N. And hence, K is quantized. Here it is. I just derived it, quantized. And so the units, it's quantized in units of delta K equals 2 pi over L. And there it is. You can just see it, because that's my integer, N. And so that means that this is going to be that here, the distance between these things is delta K equals 2 pi over L. So the smallest spacing between the different allowed Ks of your system is 2 pi over L, where L is the size of your system. This is always true. And so that's why if you have a gigantic system, the Ks are a continuum. But if you have a small system, the Ks are quantized. So that's how to think about it. So the Ks are quantized. And so then what we do is we think to ourselves, okay, well, if I define some width here, let's call this dk. Let's define some dk. Then I have a bunch of states. All these states go up. And I have all these energies. And so then that defines some energies, right? So all the states in that width dk are living in some width dE. So that means that I can think of my states either in K or E. And there's a simple way to think about it, because now I know then that I can count those states, count the states in dk. It's the same as the states living in in interval dE. So then what I say is the density of states of my system times dE has to equal the density of states of my system in K space dk. I'm making an equivalency because I can count the states in K or in E. And so where rho of K is equal to number of states, that's the density of states in K space, number of states per delta K. And what is the density of states in K? That's the easy one. This is the easy one. And it's easy because we know that we have one state per K, delta K is 2 pi over L is equal to L over 2 pi is equal to rho of K. So rho of K is always the easy one. Easy. And so that means then that we can say that rho of E is equal to rho of K, what we know, times dk over dE, because we just pulled that underneath. But dk dE is also pretty easy. And this is all pretty easy because rho of K, we know that one, it's L over 2 pi. And dk dE is easy too, because we know that that is dk dE is equal to dE dk inverse. And we know that because E is equal to h bar squared k squared over 2m, just kinetic energy. And so then we know dE dk is just the derivative of that, which is h bar squared k over m. And so then I know that I'm done, because then I know that dk dE is just the inverse of that, is equal to m over h bar squared k. Got it. Ta-da, got it. Oh, except I have a k here. But for k, we can get that because we know that that's easy to get. Ah. Fuck. It's so annoying. I'm just not worried about it. So k we can get because we know that if h bar squared k squared over 2m is E, then I know that k, I just invert that, is equal to square root of 2me over h bar. And I just plug it in. And so then that tells us that dk dE is then, do I have it written down here? Oh yeah, there it is. Then dk dE is m over h bar times 1 over square root of 2me. Not hard. It's little derivative games. And so we have these two things. And so then we put them together and we have density of states is equal to density of states. When I put it all together, is going to be equal to L over 4 pi h bar times square root of 2m over E. That's the density of states for that's the 1D density of states. And then it's different for 2D and for 3D. And you guys should see what it is for those other ones. You should derive those on your own using the same type of reasoning. And you've probably seen it in other classes. It's usually done in physics 7C, for example. Okay, so now we know, remember, we need to find the density of states at the final energy, but the final energy was the energy of the photon, h bar omega, and so that means that it's going to be L over 4 pi h bar square root of 2m over h bar omega. And sometimes there's like a factor of 2 because we have the states here, but at a particular energy, we also have the states on the other side too. So don't forget the other side. So that leads to a factor of 2 because it's in some energy range, I have the right moving states and I have the left moving states. So I should do times 2 for left and right moving states. So then we'll have a little times 2 for the directions, 2 directions. But the density of states is doubled because I can have the right moving states and the left moving states, all at the same energy. It's a degeneracy. Okay, so we have it. So then we're basically done because we see that the current in our system is going to be the charge times the number of defects times the rate, and the rate is pi over 2 h bar times the density of states of the final states times the matrix element that connects them, the initial and final states. And so we did it. We're done because we've calculated all these different pieces. Okay, so that's an example of Fermi's golden rule. So I guess that took longer than I expected, but I think it's a really nice example. Kind of steps you through all the little different ideas. Okay, so now let's do the next thing, which is broadband absorption, which is really just another example of Fermi's golden rule, but it's a little bit weird. It's sort of like an inversion. I'll call it the inverted Fermi's golden rule, inversion of Fermi's golden rule. So it's a cute example. It's in Griffith's book. I really like it because it actually is important. It's an important physical phenomenon. And so let's talk about broadband absorption. And this is actually quite important, and it's not obvious at first, because, in class we talk about this. In class we talk about, I have some quantum levels, and I have some initial state, and I have a laser which shoots a pure frequency omega at that, and then I look at and I say, what's my rate? And I say, what is my rate of, what is my probability to have a transition from my initial to final at some time t? Okay, that's what we often talk about. But in reality, the thing is, often in nature and in the real world, we don't have a laser. And in fact, typically we don't. Because remember, lasers weren't even invented until the 50s. And so, often we don't have a laser. And what we typically have is a broadband source. A broadband source of radiation. And really, quite typically, it's coming from a thermal source. It's typically black body radiation. I mean, until like the 50s, all we had was black body radiation. It's a thermal source, you know, and a thermal source is like a light bulb, right? I have a filament, a hot filament giving off light. A hot filament, that's a light bulb, or the way light bulbs used to be. Or I have a star, a burning globe of hydrogen out somewhere in the far reaches of the universe, a star. These are thermal sources of light. It's because the stars tend to be quite hot. And that's where we get light. We get light from hot filaments and stars. I mean, that's where we used to always get light, but except for these days, now we have LEDs and stuff, but there are many thermal sources. Okay, so for a thermal source, then the thermal source, like the sun, gives off broadband light. And so broadband means that there's light at all frequencies at the same time. And so we have all frequencies simultaneously. That's broadband. And that's a little bit more complicated to describe mathematically. That's why in class we always like to use a laser, because it's mathematically more simple just to talk about one frequency. Thinking of all frequencies happening at the same time, it's a continuum of frequencies. And it's mathematically a more complex thing to think about, continuum of frequencies. But in nature, it's actually a more common situation. And so we have to deal with it. And so let's deal with it. And so basically what's happening when you have a continuum source, then like the sun, then what you do is you sending out all this stuff. And so the way to think about it is that we have some, let's pick a certain volume. And so that radiation is coming at us through space. And if I just pick a certain volume in space, I can integrate all the energy in that volume of space. And so you know that I have the energy density. I can say that the total energy is equal to the integral of the energy density per volume. And that's the total energy density and then what I can do is I can say then that the total energy density, total energy density, I can say, well, the total energy density is also, I can write that as an integral of the energy density at different frequencies from 0 to infinity d omega, where u of omega is equal to the energy density per frequency, energy per volume per frequency. And so what we often refer to this as the spectral density. Spectral because it's energy resolved, spectral density. And so the way to think about it is we say that you guys know that there's a formula. We know that the energy density, there's a formula for it that you all have learned, or you do learn in some class. You should have learned it in 110 or in physics 7b. You know that the energy density for electromagnetic radiation is 1/2 epsilon naught times the electric field, the total electric field squared. And so then what that means then is that the spectral energy density this U of omega is equal to 1/2 epsilon naught E of omega squared, where that's the where E of omega is equal to the electric field at omega. At omega, but it's divided by frequency, it's divided by root hertz. Because you can see that the U of omega is energy density per frequency, and so E of omega is electric field per square root of frequency, root hertz. Square root of frequency. And that's a little bit weird the first time you see it, but that's how people talk. We talk about square root hertz. And so then we can see then that so then we can see then that E of omega from this expression, usually the way it works out in the real world is usually what we know, or we're given, I should use the word given. Usually we're given the spectral energy density, U of omega. Like for example, we know U of omega for a black body source. And from U of omega, we then can, from this expression, then we can see that E of omega is equal to square root of 2 U of omega over epsilon. Okay, so, and this is the electric field per root hertz, E field per root hertz. Okay, so that's a long-winded way of saying that, you know, that this is how we describe a broadband source. This is how we describe the E field of a broadband source. And so now what we do is let's talk about a very typical scenario. Let's say that, let's consider this. We have a sun. Let's say that we have a very thin leaf from a tree. Terrible drawing of a leaf. Let's say we have a thin leaf. And then the light goes through the leaf. And here I'm standing and I'm looking at it with my eye. And then the light comes through the leaf into my eye. And then the question is, what color do I see? And so that's what we got to figure out. And so the idea is that the sun is shooting out all frequencies of light. And let's think of the leaf as a little box. And let's assume that the leaf is a little box. Leaf is a box. You know, like I like to think everything is a box. So I have my initial state, and in my leaf, I only have 2 states. So this is a pretty simplified leaf. My leaf has a final state and an initial state, and I'm shooting all these photons at it, but some of them are getting, and there's an energy difference here, delta E. And so some of them are getting absorbed. And so then what is happening? How does this work? What is happening um, some of the light gets absorbed, and what comes, so light is absorbed, and then light is transmitted. And so the light transmitted is equal to the incident light minus the light absorbed. And so the incident light is described by U of omega, which gives us E of omega. But what is this? What is the light absorbed? That's what we want to know. How much light is absorbed? What light is absorbed? How does the light get absorbed? Because the light that's transmitted determines the color of the leaf. And that's the question I'm trying to answer. All right, so I know the incident light, but I got to figure out what is the light absorbed. And so that's the situation that we want to calculate right now. What is the light absorbed? And so let's figure it out. And so basically what is happening is that I have some initial state described by some initial wave function. I'll just call it phi I of, well, let's just call it phi I just to make the initial state. And then I have my final state described by some final state. And they're separated by some energy difference. And I want to know what are those transitions. So I want to know what's the probability of a transition. So here I'm shooting broadband light at it, described by some U of omega, spectral density. And the question that I want to ask is, what is the probability that I have a transition from my initial to my final state at time t? So I turn it on at time 0. I turn it on light at t equals 0, then what is probability of transition at time t? Okay, and so this is a setup for perturbation theory. And so what we do is we realize that the probability, the thing is that every frequency of light will independently induce some probability of transition. So the probability of transition is the sum of the probability of transition for every frequency. Because every frequency, and that's the big insight, like every frequency of light is like a feather that's tickling you. It's like, what's the probability you're going to sneeze? Well, if someone is tickling you with 32,000 feathers, it's like each feather is going to give you a probability to sneeze. And so if someone's tickling you with 32,000 feathers, tickling your nose, then you just say, okay, what's the probability of me sneezing from every single feather? And I add it all up, and then that's the probability that I will sneeze. Okay, so that's a nice way to think about it. And so we got to add up the probability to sneeze from every feather, every omega. And so then the question is, what is the probability that I have a transition from the initial to the final state due to the light at a particular frequency, omega? And it just so happens that you know that. You know that result from time-dependent perturbation theory. It's a simple formula that we figured out. It's this formula that we derived in class. It's the matrix element of the perturbation that takes me from the initial to the final state squared times sine squared of your energy of your final state minus the energy of your initial state minus the frequency of the sinusoidal perturbation times time over 2h bar divided by that same thing in the denominator, EF minus EI minus h bar omega squared. We derived that. So that's a formula. That should look familiar. It's that diffraction formula. You know, we derived it. So that means then that, and you know what all these terms are. You know that, and you know what that matrix element is. H prime, the matrix element is just going to be your optical matrix element. It's just going to be your final state. And you know, for light, because we have the broadband light hitting it, you know it's going to be charge times electric field. But because it's the omega, then we know that it's going to be the electric field at that frequency, omega dot r, the position operator in that matrix element. Okay, and so then we can write it like this. We can pull that electric field. We can do what we did before. What I just did, I can pull the electric field out, dot it in with the final state minus E R initial state, and then I can call this thing is my dipole matrix element, and so this then becomes, oops, let's not square it just yet, and so then I can see that H prime Phi is going to be equal to negative E of omega dotted with P F I. That's my dipole matrix element. Okay, and so then if I have, let's assume that my light is polarized. I have a polarizer. Let's assume that E of omega is equal to E of omega z hat. And so then H prime Fi is equal to minus E of omega Pfi, the scalar, where Pfi is equal to just this, just the z component, minus E z phi initial. Okay, so and let's assume that we know this. Because I know the initial state, I know the final state, and I know z, it's a function that I know. And so then that's a known quantity. And so then what we can do is we see then that so then we see that what we have is that the probability to have a transition from the initial state to the final state at time t is going to equal the sum over all the frequencies of the probability to have a transition for all the frequencies. And so that's going to be then, I have to sum this quantity up that I just described. And so it's going to be this thing h that times that sine function. So I got these two things. I got the product of these two things. And so let's multiply them together. And so I see that the matrix element is this. And so it's going to be E squared of omega times P Fi quantity squared And then I have to multiply times that sine function, sine squared EF minus EI minus EI minus h bar omega times t over 2h bar over F minus EI minus h bar omega quantity squared. Okay, so that's it. And so then what we'll do is we'll use, if we know the spectral density U of omega, then we'll use this relationship, which is that we know that U of omega is equal to 1/2 1 over 2 epsilon naught times E of omega squared. And so we'll use the fact that E of omega squared is equal to 2. Whoops, I got this formula wrong. It's equal to 1/2 epsilon naught E of omega squared. So E of omega squared is equal to 2 over epsilon naught U of omega. All right, just a little formula. And so that means then that we plug that into here. And because U of omega is a spectral density, and because this is actually a nice part, that's an energy density per frequency. So then we can immediately convert our sum into an integral. That's the beauty of it. So then we can convert sum into integral easily. We don't have to do the density of states business because it's already built. The density of states concept is already built into that spectral density. And so then we see that Pfi of t is equal to the integral of all the frequencies times, let's put it all in there. I'm going to have 2 over epsilon naught U of omega times P the dipole matrix element connecting initial and final states times sine squared F minus I minus h bar omega over t times t over 2h bar all over EF minus EI that's h bar omega squared. And it's integrated over d omega over omega. Whew, okay, so we converted the sum into an integral, and now we have it. And so that is the probability to have a transition. So now we have to do this integral, and it turns out that that is a harmonic integral. You think, oh my God, it's so hard, but it's not. It's not hard because we remember that this function, we already sort of worked this out. We know that this function is highly peaked if I plot this function, it's highly peaked at omega is equal to it's highly peaked at h bar omega equals the difference between the initial and final energy. Because remember, this function looks like this. We've plotted it before. It looks like this. Where this, if I plot it as a function of h bar omega, then this point right here will be F minus EI. And so it's highly peaked at where H bar omega equals EF minus EI. And we know that this thing gets bigger with time as a function of time squared, and it gets narrower. The width goes as 1 over time. So it's highly peaked as time goes on. And so then what that means then is that we can start bringing things out of the integral. We see that this thing can come out of the integral. The dipole matrix element between the initial and the final state, because that does not depend on frequency. So pull it out of the integral. But this does depend on frequency, this U of omega, the spectral density. But we see we can bring that out of the integral also. The reason we can bring that out is because of this highly peaked nature of the integrand. So that means that U of omega goes to U of one particular frequency, U of omega naught, where omega naught is equal to, where H bar omega naught is equal to EF minus EI. And so omega naught is just going to be 1 over H bar times that. Okay, so then we have that. And so that means then that now our integral can be rewritten as the probability to have a transition from the initial to the final state at time t is going to be equal now to 2 over epsilon naught times u, but now at a special frequency, which is going to be the EF minus EI over H bar, which is omega naught, times the dipole matrix element, which does not depend on frequency. It just depends on those two states, the dipole matrix element connecting those two states. And now I have this integral from 0 to infinity of d omega of sine squared EF minus EI minus H bar omega times t over 2H bar, all over EF minus EI minus H bar omega squared. And we have done this integral. It should look familiar to you. This is the same integral that we did as for Fermi's golden rule. Same as for Fermi's golden rule. We've done this integral before. That's a key thing. That's why I call this an inversion of Fermi's golden rule. Because instead of having a continuum of final states, we have a continuum of perturbations. The mathematics is exactly the same, but it's a funny inversion. You should think about it. And so to do this integral, we do the change of variables. Remember, change of variables. And so what we do is we define a new variable. C is equal to EF minus EI minus H bar omega times t over 2H bar. And so then we have dc is equal to negative d omega over times t over 2. And then you plug back in, and then you plug in your change of variables. And then what we end up with is, is that the probability to have the transition from the initial to the final state of time t is going to be equal to, plug it all in, you get 2 over epsilon naught times p dipole matrix element times u over EF minus EI times t over 2H bar squared. We have this integral, and because of the change of variables, it's going to be will actually be, well, we're going to do, it's actually ever so slightly tricky. It's not that tricky, but this is the integral when we do everything carefully. Sine squared c over c squared. And so then what we do is we do this. We say, well, this is the same. Since this is an even integrand, we say that this is the same as times 1/2, and then we change this into plus infinity. So we doubled the integrand, and then we just multiplied by 1/2 because it's an even integral. And so then we can see that this integral is our old friend pi. There it is. And so then what we get is we see that p, the probability as a function of time then becomes, we have that time, and it just becomes pi times t over 2 epsilon naught h bar squared times the dipole matrix element. And so times the spectral density at that transition frequency. And so then we see that this is a transition rate equals a transition rate times time. Because you see we have the time there. It's linear in time. And so that means it's a rate because it grows linear with time. So it's a rate times a time. And so that means then that the rate, transition rate, is equal to this probability divided by time. So I just divide out the time and I have the transition rate, which is going to be pi over 2 epsilon naught h bar squared times the dipole matrix element, p phi squared times u at that special frequency where that's equal to EF minus E initial over h bar. And so that's the rate of transitions, the rate of transitions. And so we can see that the transitions are happening. So we can see that so what's happening then is, remember the initial setup was I had the sun, which is sending out some broadband U of omega to my leaf, which was shaped like this. You know, it's a leaf. And then the light came out, and so what you can see is that this light is absorbing at EF minus EI over H bar. And so what comes out is going to be U of omega minus U of omega naught. So basically that frequency gets absorbed. And so the color, and that's color, because suppose U of omega naught is red. That means that the color, I have broadband light, which is, suppose U of omega naught is red, and suppose that U of omega is white light coming from the sun. And if I'm sucking out the red, then what's left? Green. And so what I see is a green leaf. All right, because the leaf absorbed the red light from the sun via this process. And so that's very, so the colored light is transmitted Okay, well, that's a nice way of thinking about it, I think. And so the important thing to notice is that the rate of transitions, the rate of absorption is, you see here, I had the rate of optical absorption from a broadband source was proportional to the spectral density. Let's go back to that formula. It's the spectral density, which is playing the same role as the density of states before. But it's also times this dipole matrix element. And so notice that this PFI, which is equal to the final state, and then I have the dipole matrix operator, which is for an electron, it's just the charge times the position of the electron. This is the dipole matrix element. I want you to appreciate the important role played by the dipole matrix element, which connects the initial and final states. And so this dipole matrix element is really important for optical absorption. And so this leads, and so the fact that the rate of optical absorption is proportional to this dipole matrix element squared means that to understand optical absorption, we have to understand this this dipole matrix element. And so there's a very important concept, which is that which is that the rate of absorption equals 0 unless the dipole matrix element does not equal 0. In other words, it turns out that often in our in physics, there is symmetry. And then this symmetry can cause matrix elements to be 0. And if the matrix element equals 0, then we have no transition. And so the question is, when we have to ask ourselves, when is the matrix element 0 and when is it not? And so this leads to the concept of selection rules. And so it looks like I don't have time to derive all this stuff, but I'll just sort of set it up and then we'll stop. The idea is basically, let's consider atoms. And so for atoms, what we have is we have the states are these atomic orbitals, N, L, M. And so then for atoms, we'll have some initial state, and then we'll have some final state. And so then for an atom, we'll have some dipole matrix element connecting the initial and final state. So absorption is going to be proportional to the dipole matrix element connecting those states. And so we have to figure out what is this quantity. And the point is that symmetry often makes it 0. Except for special values of NLM and N prime L prime M prime. Certain you're going to get 0 except for special values of the initial and final state. And this whole concept is we call that a selection rule. And we will derive what that selection rule is, but not today. Okay, bye-bye.